Today, we are diving into something that sits at the very heart of all science. We're talking about measurement, or as you'll see here, la misura. Now, it sounds simple, right? But it's really a quest, an adventure even. It's all about taming a little bit of chaos to find one single, reliable piece of truth. So, let's get into it.
Okay, so picture this. I give you what seems like an incredibly easy task. Something you've probably done 1,000 times, without even thinking about it.
That's it. That's the whole job. Just measure this object. You'd grab a ruler, line it up, scribble down a number. Job done, right? Well, maybe not. Because the second you write down that number, a much, much deeper question pops up. How much can you trust that number? How certain are you? And look, this isn't just some textbook exercise. This is the fundamental challenge every single scientist grapples with. How true, is the truth you think you've just found?
To even begin to answer that, our whole quest has to start with a choice. Before we can measure a single thing, we have to pick our tool. And this is a huge first step. La scelta dello strumento, the choice of the instrument.
And right away, that first big choice is often between analog and digital. Think about it. Analog tools like your classic ruler or a dial, they have a continuous scale. It's up to you to interpret where that needle is pointing. But digital tools like a caliper or a multimeter, they just flash the numbers right at you. So one needs your judgment, the other gives you this crisp, precise number. But here's the thing, neither one is better. They're just different tools for different situations.
Now, every instrument has its own spec sheet, its own personality. The first thing you have to know is its portata, which is its measurement range. Basically, the biggest thing it can possibly measure. I mean, it's pretty obvious when you think about it, right? You wouldn't try to weigh a car on your bathroom scale. The portata just tells you the absolute limits of your tool's world. Next up is sensibilità, or sensitivity. This is the absolute smallest tick mark on your instrument scale. It's the finest detail it can possibly see. So if your ruler is marked off in millimeters, its sensibilità is 1 millimeter. Period. You just can't pretend your measurement is more precise than that. And finally, there's prontezza, or its readiness. This one is all about speed. How fast does the instrument lock onto a stable, final reading? If you're trying to measure something that's changing fast, like the temperature of water as it boils, you need an instrument with high prontezza that can keep up. You don't want a tool that's slow and laggy, giving you a reading from 30 seconds ago. So we've picked our instrument, we've made our first measurement, and now we have to enter the next stage of our journey. We have to confront the dragon that lives in every lab, the unavoidable, undeniable reality of uncertainty.
Let's just get this out on the table right now. This is like the first commandment of the lab. No. Measurement is perfect. It just isn't. Every single one, no matter how careful you are, is going to have some little bit of error, some fuzziness to it. So the goal isn't to get rid of it, because that's impossible. The goal is to understand it and to put a number on it.
These little imperfections come from a few main places. First, you've got errori sistematici. Think of these as a flaw in your setup, like a scale that's always off by 1 gram. It's going to push all your results in the same wrong direction. Then you have errori casuali, random errors. These are the unpredictable little flukes, like a tiny gust of wind or a vibration that nudges your reading. And of course, you've got simple human slip-ups, like errori di parallasse. That's when you read a meter from an angle instead of looking at it dead on.
Okay, so errors are a thing. But let's be realistic. What happens when you only get one shot? You can only make one measurement. How on earth are you supposed to estimate your uncertainty then? Well, for that single measurement, we have a handy little rule of thumb. It's called the semidispersia massima. It's like a first aid kit for your uncertainty. The common way to do it is you just take the instrument sensitivity, that smallest little tick mark, and you just cut it in half. That gives you a pretty decent plus or minus range for your single data point. Is it perfect? No, but it's an honest start. So, a single measurement gives us a rough idea, a ballpark figure. But what if we could get more, a lot more? Well, in this next section, we're going to learn the statistical techniques we need to tame all that random noise and get a much, much sharper picture of the truth. And here's the real game changer. A single measurement,
It's really just a lonely guess floating out there in a sea of uncertainty. But if you repeat that same measurement over and over and over, all those random little errors, they start to cancel each other out. And suddenly, out of all that noise, a pattern begins to emerge. That, my friends, is the power of doing the experiment more than once. Our number one weapon against random error is the valore medio, which is just a fancy way of saying the average or the mean. You know how to do this. Add up all your individual measurements, then divide by how many you took. And this new number, this average, which we represent with the Greek letter mu, is now our single best guess for the true value we're after.
Now, check this out. This is where it gets really cool. If you take all of your measurements and plot them on a histogram, you'll start to see them stack up. Most of them will pile up right around that average value you just calculated. And this beautiful, classic shape that starts to appear, well, that's the famous Gaussian distribution. You probably know it as the bell curve. It's like the natural signature of data that's been shaped by randomness. But knowing the average isn't the whole story. We also need to know how spread out our data is. How reliable is that average? For that, we use the scarto quadratico medio, or what we call the standard deviation, represented by the Greek letter sigma. This number is unbelievably powerful. It tells you exactly how wide or narrow that bell curve is. A tiny sigma means your data points are all clustered together, super reliable. A big sigma means your measurements were all over the map, and your uncertainty is pretty high.
Okay, we have done the hard work. We picked our tool, we faced down our uncertainty, and we tamed our data. Now, it's time for the final crucial step, presenting our discovery to the world in a way that is honest, clear, and totally scientific. The first rule of presenting your data is honesty, and that begins with arrotondamento, or rounding. You have to round your final answer so that it reflects the real precision of your measurement. Claiming a bunch of extra digits that you can't actually justify, that's a huge no-no in science. So we just follow the simple rules. If the last digit is 4 or less, you round per difetto, or down. If it's 5 or more, you round per eccesso, or up. And this same idea applies when you do math with your numbers, using what we call cifre significative, or significant figures. Just remember the old saying, a chain is only as strong as its weakest link. So when you add or subtract your measurements, your answer can't have more decimal places than your least precise number. And when you multiply or divide, your answer can't have more significant figures than the number that had the fewest to begin with. And all of that, the rounding, the sig figs, the statistics, it all leads to this. This right here is the grand finale. This is how a real scientific result is presented. It's not one single number. It's a statement of confidence. It's the mean plus or minus the uncertainty, the valore medio plus incerteza. It's you saying my best guess is this number, mu, and I'm confident the true value is somewhere in this range, from mu minus sigma to mu plus sigma. It's beautiful, really. It's a statement of knowledge and humility all at once. And this is where it all comes together in a picture, on a grafico sperimentale. You don't just plot a single point anymore. No way. You plot your result with its barre di errore, its error bars, that visually show the true range of your finding. And this becomes the ultimate test. You can draw a line on that graph that represents a theory, a legge fisica, a physical law, and you ask one simple question. Does my theory's line pass through my error bars? If it does, you've just found evidence that supports a law of nature. So in the end, you see, measurement isn't really about finding the one right answer. It's about this incredible process of confidently, honestly, defining the range where the truth most likely lives. It's about truly understanding the boundaries of what you know. So now that you know how to do it properly, what are you going to measure next?